So, thanks everybody for coming, and so it's a great pleasure to welcome Konstantin Klemm the day after his birthday. So probably most of you know Konstantin is as I usually say, is a permanent visitor. So he basically comes every year to spend a couple of months. And this time he will be here till the end of March. And so we have been working together for several years. Yeah. And topics on opinion dynamics, the bottom model, on networks, epidemic spreading, this kind of things. But today he's presenting something else. So you can read from here. I mean, he's coming from Leipzig University, and he's in the group of Peter Staller that probably some of you know. So thanks, Konstantin.
Yeah, thank you for the kind introduction. Very happy to spend time here with you again. So this is work a little bit in the grounds of computer science also, just to fulfill the requisites of my affiliation, but also pertaining to evolution principle. It's the idea to, as done in many contexts, to see evolution as optimization. So then it becomes interesting to take over some principle that we may have understood in biological evolution to optimization. And if you accept that to some extent biological evolution might serve to optimize something. People may doubt that. Anyway, good. But also we thought that there was some physics in that, so actually we tried first to get it into a physics journal, where we then, after the submission, we were very surprised that on the status page it didn't say interdisciplinary physics as we had chosen, but the editor had chosen to put it into condensed matter electronic properties. And this is also how it was reviewed, the result that it was not physics, and so now it's almost accepted in Kosovo. And since the two referees there liked it immediately, I thought, okay, this would be fine also for a presentation here. Good. So I will talk about, concerning the computer science problems, I will talk about three of them, which are number partitioning, maximum cut in a graph, and the traveling salesman problem, where the first two are basically, well, in physics terms, sort of spin glass problems, but in order not to give you too much of computer science at the very beginning, I will restrict myself to the number partitioning problem, and that can be put into the following real-world scenario. So imagine that two burglars have just cracked the safe, they've opened the safe, and now in front of them they have a big pile of valuable things, all sorts of things, coins in different currencies, maybe stocks from Spanish airline companies, Greek government bonds, and so on. And, okay, they are experts, so they know exactly the value of each single item. This would reduce the problem size at least. And they're also pedantic experts, so they want to have an absolutely fair share. This should be shared as fair as possible. Okay, so you have they have these values here, and now, of course, items cannot be split. So they have to decide who takes what, such that total values taken are as equal as possible. And then the question is, okay, can they do this quickly in situ because they want to leave in separate directions afterwards before the police come? They want to do it fast. Good. Maybe you can already start thinking about that, how you would do it. Well, I define the problem slightly more formally, so you're given a list of positive integers, and the decision problem, first of all, is can they be shared equally in a fair manner? So can you put these items on the left and on the right such that the sum of values on the left and the right are exactly the same? And the optimization problem, because maybe you cannot do this. One obvious case is that these sum up to an odd number, right? Then you want to find a true partition that gets as close as possible to equal sums. So here, for instance, you can do it for these values 8, 7, 6, 5, 4. One of the burglars just takes 8 and 7, and the other takes the rest. They both sum up to 15. Good. Heuristic algorithm might have come up with, actually 2 computer science 30 years ago came up with this idea, is, okay, let's do this sharing iteratively, and let's say that perhaps the 2 most valuable items, they go to different people. One doesn't take the 2 most valuable items, but they, in any case, have to go to different people. And then, assuming that this leads to an optimal solution, which is not always the case, as we will see, then we can replace the problem by a smaller one, namely by simply replacing these 2 items by their difference, right? Then we say, okay, each of us already got 7, and then there's 1 left, which is distributed by deciding who actually got the 8 and who got the 7. So assuming that 8 and 7 go on different sides, this is the remaining problem, okay, which I indicate here by connecting them with sort of an inhibiting edge. Okay, then this is your remaining problem. Then again you take the ones that are now the 2 most valuable, and this comes to 4, 1, 1. Now 4 minus 1 is 3, and then in the end there's nothing to choose anymore, it's 3 minus 1 is 2. Okay, so this algorithm in many cases works surprisingly well, gets surprisingly close to the optimal solution, but this is the same example as we had on the last slide, and there I showed you that the answer to the decision problem is yes. So you can make an absolutely fair sharing of this by having 8 plus 7 and 6 plus 5 plus 4. So here is already an example where it fails. I think it's actually the smallest example.
How come the story? So you say 8 and 7 are on different sides, but they are not in the optimal solution.
So this is a heuristic that tries to be fast and sort of accurate.
So what is the partition then at the end?
Okay, now you have to backtrace. So we know that
Okay.
I didn't. I mean, then this picture gets even more complicated. Well, in principle, these edges that I drew here, they indicate things that are on different sides.
Yes.
So 7 is on different side of 8, and 8 is on the different side of 4, so 4 and 7 are on the same side, and 4 and 5 are on the same side. So it comes up with 7 plus 4 plus 5 and 6 plus 8. And then you have 14 and 16, and the difference is 2. So just to make clear, this is sort of a quick and dirty method. It doesn't need to work, but this is maybe good for these burglars because they have to finish the job quickly, and so it's not quite optimal. So, and in fact, you could have.
Konstantin,
Yes.
go to the project. But you have to do this on 3, right? Because you have a link between 7 and 8. But
Yes.
how you decide that you have a link between 8 and 4 and not between 4 and 7?
Because
You have-
okay. So well, let's go.
Well, I don't know if this is a problem.
Yeah. So let's get all these details up.
Okay, let's really understand the thing. So, so I know that where this inhibition here, so to speak, or this negative edge or whatever, I know that these two are on different sides. Okay. Also here, there's no problem. So now comes this combination where I had 5 and 6 on different sides here, being represented by a difference of 1 over there. And now I make the difference of this 1 with the 4. And so the largest one here, the largest side here, has to go on a different side than this one.
It's always not the rule.
Yeah, okay. I mean, you can,
Okay.
this is now graphically, I mean, you can write down the back tracing really systematically. So there's you always, I mean, when you found the supposedly smallest difference here, then you can also find actually a partition that implements this. This is cool. And you can just, okay. I don't have the algorithm here now, the back tracing, but in principle. Good. Also because, I mean, practically you see how that works, right? So you only decide, okay, this goes on a different side than this, so you can really distribute your stuff spatially, and then you know which is on what side in the end.
So algorithmically seems easy, but in order to do it in the real example, it's complicated, right? Because you have to throw the things there and do the network and then split it. Anyway.
No, okay.
Yeah, no, go back.
Good. So this problem is NP complete, so which means it's easy to check a little solution once you have it. You can check a given solution in polynomial time. For instance, if somebody gives me a solution where it says this is absolutely fair, so the answer to the decision problem is yes, and here is a certificate of that, then I can check that in polynomial time, and you just have to do the sums on both sides.
You cannot find the solution in polynomial time.
You can check solution in polynomial time
You can check.
by a certificate. I mean, just somebody tells you, okay, put this and this and this on the left and that, all the remaining stuff on the right, then I can check whether this is okay. But it's probably difficult to find it. Okay? So it's not clear whether really there is no polynomial time algorithm for doing that. Polynomial in the size of the problem and the number of items. But this complete means that out of this class of problems, this one belongs to the hardest in principle. Anyway, for more like a physics interpretation, you can write down an energy or a cost function, which is like this, right? For each item, you just define a prefactor, which is +1 or -1, just like a spin value that you put in front of it. And then you want to have as much value with a minus sign as with a plus sign. So this is your cost function, and if you have found a partition that is absolutely fair, then the cost function is 0.
So basically the cost function is the difference between what what the two people did.
Exactly. And now if you say these xi, these minus ones and plus ones are spins, then this is, you can basically say that this is a sort of spin class. If you square your cost function, then you have a spin class like this with your coupling, where your couplings are the minus the product of the values, right? Which doesn't prove that this is difficult. I mean, even if you have accepted that maybe it's difficult to find the ground state of a spin glass, of course this is a very peculiar kind of spin glass, so this wouldn't have to be difficult, but it has been chosen in a different way, that it is really, that there's so much frustration in the system that it is really hard to find an optimal solution. And that's also the reason why this very simplistic approach with the differencing that I showed you before doesn't always give the right solution. It was rather surprising that it worked so well in many cases, which I haven't shown you now. Good. So then let's try something different, and here comes the evolutionary part. Maybe we can get better not by formulating this difference heuristic, but iteratively improving the solution, right? Somebody has a reasonable solution already, but the difference is not zero. Maybe by somehow mutating it, you can make it better. And this looks a bit like evolutionary optimization. So maybe you have a population of solutions which are the individuals. They all look different, and then they can reproduce, and during the reproduction there are some deviations from the kind of solution that you have. So some of them just by chance make it better, and due to selection you can sort of save the better solution and forget about the rest. So the survival of the fittest idea. Good. And I want to use this idea to formalize a bit more such kind of scenarios in terms of a landscape, and this will allow us to treat this kind of optimization problems in a bit more general sense. In fact, in biology or in genetics, this idea of a landscape already came up in the 30s of the last century. So the picture is maybe you have a wild type, sort of the original genome, the original genetic code, and then there can be mutations in certain places. Okay, like one individual in the population gets a mutation in A, so it has a variation in locus A, and another one has variation in locus B, and then they can also accumulate. So you can have both together. And then you can increase the number of loci. So Wright drew this in his paper. He drew this up to 5 loci, and then, but already at that time they could actually, don't know how they did it, but they could actually detect up to 1,000 loci where individuals in the population, in this case it was this fruit fly, Drosophila, showed some mutations, showed deviations from the wild type. Okay, so this would be sort of the substrate for a typical combinatorial landscape. In this case, it's just hypercubes, right? Cubes in different dimensions. Good. So more formally, mathematically, so to speak, a landscape is made out of 3 things. Your state set, the set of all possible solutions, and for the spin problems, that would just be the +1, -1 vectors of length n. Then you have to somehow say what your mutations can do. So this is what we call the move set. So each node or each state here has a set of neighboring states. Okay, so formally this x maps to the power set of x. So for each x, for instance, for this one here, I have to say what the neighbors are. Maybe in this case for AC it's A, C, and ABC. And then I have to define something like fitness that enters the selection or the distinction between good and bad solutions, and that is just a function that assigns each possible solution a real value.
Konstantin, sorry. In this representation, A and B, I understand, are possible solutions of the problem, no?
Well, the possible solution is here is saying for each letter whether the given individual has it or not.
Okay, so
having it would be a +1 at this position, and not having it would be a -1.
So if there are, I don't know, 20 items to be shared, there will be 20 letters?
Yeah, which would mean I have each individual is characterized by a vector with +1s and -1s of
It
length.
should be the letters that they have,
Yeah.
the letters that the individual have. And then the path is the way that they have been distributed, so the path represents the way. So first this one goes A, the other one goes B, or something like that.
Yeah, that would already
I
be.
mean, the path in this diagram that...
Well, that would already be an evolutionary path. Yeah. So exactly, if you say, okay, how could I have come here since maybe mutations don't happen synchronously? Maybe I got first A and then B, or first B and then A.
But at intermediate state, you have not already distributed all the items, only part of it.
Okay, now
So the evolution, I mean, there is
So
two
the
ways to...
evolution is mutating the vector, mutating the distribution, changing one item from one place to the other.
Right, but then A should represent a full solution. Not...
Well, just saying A means A is there and all the others are absent. Right? So, I mean, if I have so A in the spin representation would, if you say it's there means +1 and it's not there means -1, then it would be this one, because A, this means presence of A is there,
so
B and C are not there, right?
So then, starting from plus, from the initial point, at the first stage, you have 2 to the n possibilities, because it's all the possible ways, or what
Well, you have
a big combination of all the possible solutions.
Well, on the landscape you have n neighbors because you can change.
Yeah, but there is a solution. So I have
Yeah.
3 items, 2 people, or 4 items, 2 people. I can distribute in different ways.
Yeah.
N is one possible way of distributing. B is another one. C is another one. There are many of them. 2 to the n.
Yeah. Yeah.
And then you take one of these solutions and mutate and distribute some. I mean, so you don't take all the 2 to the n. You take a fraction of that. Say, well,
Okay,
I'm
that
going
comes,
to- okay. Cool.
that comes now. So now,
Okay.
what kind of evolutionary dynamics do we want to consider? And to make it simple, actually, I don't model a detailed population. What I do is an adaptive walk. So in physics terms, that's a zero temperature Markov chain, which means we have a homogeneous solution, so all of them have the same state, and then there's a mutation in one of them, which takes it to a neighboring state. So I'm at state X, and then remember this M was the move set, so this is a neighbor of X, Y, and if that neighbor is better, then or immediately the mutation fixates. So all of them now, I mean, the old ones die basically because the Y is better. So only the Y reproduces in short terms. Okay, whenever I suggest a neighboring solution that is better than this neighboring solution, better or equal actually, is accepted, and otherwise I stay here. So that's basically Markov chain metropolis at zero temperature, if you like. Yes, and okay, this is an idealization in the case that mutations are very rare, but when they are there and they are beneficial, then they fixate immediately. So which means that my population that is evolving is basically sharing the same state all the time, and when one of them assumes a new state that is better, then they all agree with that. Good. Coming back to our optimization problem, let's try that. We have to find what kind of dynamics we want to use now. Also, we have to find the fitness, which is the cost function of this number partitioning problem. And the neighborhood structure is just this hypercube structure. So in every step, I can decide to put one item from one side to the other. That means good. So let's just try that for some random instances of number partitioning. See what adaptive walks do. And okay, plotting energy as a function of time. Because the energy goes down or the cost goes down, but then somehow this stops. Obviously, when there are no more neighbors that are better. When I get stuck, then the adaptive walk just has to stay in that on that state. When there are no neighboring states with lower cost, cannot go down anymore. And okay, this, as we also see, this doesn't outperform, this actually performs much worse than the comparison we have here in terms of the differentiating algorithm.
Because you're always starting from the same initial conditions, or you are distributing also the initial conditions in this operation?
It's a distribution. The fact that they are all basically with the same energy is because of large numbers. So in principle, almost all randomly chosen initial conditions have the same cost. It's not exactly the same cost as a certain width here, but in principle, yes. Good. So, or not good. This doesn't work.
So you want to check whether this is better than this fancy algorithm?
Yeah, just the naive idea. Why don't we use something very simple, evolutionary, and maybe that gets better than the differencing algorithm.
But this KK was the algorithm.
Yes, yeah, exactly. So here I've rescaled the energy such that 0 really is the ground state, and 1 is this Kamaka-Karp, so this differencing algorithm that I showed in the beginning.
But I guess that depends also on what is the initial condition that you put for the second.
Yeah, random.
Yeah, but imagine that you are starting with the good partition.
For instance, you could start. Why don't you combine the two things? You could ask, right? Why don't you just start here? I mean, just.
Yeah, because that's not exact. So if you start with that one and then combine, you can get that.
What turns out is then that you just stay here because basically always this solution from the differencing algorithm is a local minimum of your landscape. So it doesn't. So the adaptive walk doesn't improve it anymore. So in principle, in the lower energy part of your landscape, it's full of local minima. Once you've found something that has pretty low energy, you can be almost sure that this is already a local minimum. Good. Okay, so then what can we do? Well, either forget about the idea, right? I mean, maybe nature doesn't really optimize in this very strict sense. There's no need for it, right? I mean, nature just maybe produces living beings that are a bit better than the others once in a while, and then these are the ones that survive, but there's no need for any evolutionary mechanism to lead something that is really globally optimal. Then you can also embark on modifications of this algorithm, like simulated annealing, right? So once in a while you allow for a slightly worse solution to be accepted, and then you can slowly walk over mountains, and maybe behind the mountain there's there is a deeper valley. This would certainly improve this here. But sticking to this idea of well, following something analog to okay, here's let's skip this. Of doing something with optimization in terms of evolutionary biology, there's maybe one thing we overlooked, and that is, okay, what is actually selected for, and what is where does the mutation take place? So in living animals, there's a sequence of letters, so to speak, that we believe codes for most of the animals or the plants' properties, genetic string, and then that serves to do something. For instance, to encode for a molecule, like an RNA here for simplicity. Okay, so this thing is. Well, this is actually not the sequence because the letters are not exactly the same, the DNA and the RNA, but never mind. So this one, if I sort of construct this as an RNA string, then it falls into this structure here. Okay, so there are some bonds that close, and what do I mean? It falls into the structure. It could do lots of things, but this is the minimum free energy structure. So most of the time, you will see it folded like this, with these hydrogen bonds here, giving it minimum free energy. Good, now I do a mutation. I replace this U here by C, so this is this one, and nothing happens, right? So it's exactly the same minimum free energy structure. Actually, the minimum free energy itself is even a bit lower because this pair has lower energy than this one. Also sort of seen from outside, so what could actually actively bind and be sort of bioreactive here in this small example is also still the same. So this would fit as a key to the same lock as before. So this is a neutral mutation. I changed something in the genome, but basically I get the same thing as before. I do get the same thing as before, only that this is slightly more stable. Good, and then I can do a mutation in a different place, so I replace, put a C here, instead of the G that I had before. Oh no, what did I have before? Well, anyway, the mutation is here, and now the minimum free energy structure is something completely different. Just because now there's this favorable GC binding here, which was not possible before. And now the shape looks different because the dangling stuff is here is on the other side, and in particular also what could bind to something else has a completely different sequence. Now it's AUCC rather than CCUU. Good. So to just say that again, the substrate on which the mutations take place are not the phenotype, the things that you actually see, but they are the sequence, but they how fit this thing is, how well it serves a given purpose, for instance of binding to something else, that is given by this phenotype. So this, in this case, the secondary structure. Okay? So the picture is slightly more complicated. You do your mutations on one thing, and then you map it by something complicated here, well, this folding process to a minimum free energy structure. You map it to something else, and that thing then determines how fit it is. Right? So genotype space are your sequences. Then there's a complicated mapping alpha that maps it to a phenotype, a structure somehow, and that has a fitness that is responsible for the selection.
So how is defining a more sophisticated fitness function?
Huh?
I mean, somehow a more sophisticated fitness function is the composition of F and alpha. And that's, you could avoid that. You could avoid this phenotype spice, just define it a more sophisticated fitness that depends on Y.
Sure, yeah. So instead of, exactly as you say, I mean, instead of having first alpha and then F, I can just compose.
Because each Y gives a single X. The same X can have several Y's, but each Y can give only one X. No?
Yes, this is a function exactly. Yeah.
This is
It's a it's a right unique relation. Yeah, exactly. Yes. So was it something else what I said, or was it?
No. It's just that this. Well, I understand that in biology the phenotype has a meaning because you really see how the animal is or how the plant is, but in here it is just a mathematical characterization that you are going to apply to one, whether this mutation is good or not, but you don't really see this phenotype.
Well, now the thing is that you can have. Now of course it all. Whether this gives us any advantage for optimization or any new insight really depends on how you define this alpha. Right? So, first of all, okay, you can make your genotype space much larger than the phenotype space. This is true, for instance, for these RNA molecules. There you have exponentially more sequences than structures. And then you can have something like neutrality, for instance. So, that is, you do mutation, but nothing happens, so you can walk a long way in your space without changing your fitness, and then maybe suddenly you find a better solution. Okay, so this is the idea. Good. So I started at 3 as usually, right? So I have plenty of time. Good. So maybe we just have to skip the other examples. Good. So now there was an idea of how to apply this to make such an encoding. That's what I forgot to mention here. So in biology, this alpha is called the genotype-phenotype map naturally, and now for optimization we call this an encoding. I encode my space of solution by something larger. Good. How do I do this for the number partitioning problem? I choose a much larger space. Now I still have n coordinates, but now in each place I cannot just put +1 or -1, but I can put any number from 1 to n. And the idea is to sort of, as the name says, pre-partition my set of items by saying, okay, I want this old watch and the coins to be in one group in any case. Okay, so these burglars, maybe they have some extra constraints what they want to have together with what else. So before starting to actually divide things, they first determine which things should in any case go together to one of them. And this is done by assigning a class number to each item. Right? So if I'll just go to the example here. So same example as we had before. Values 8, 7, 6, 5, 4. Maybe they, in the beginning, this would be the lucky choice. So somebody already says I want 8 and 7 to go together in any case. So they put it in the same class, and the other ones can be in different classes. Okay, so then now you apply the differencing algorithm to the reduced problem, which says 8 plus 7, because they go together anyway, and then set 6, 5, 4, and then of course the correct solution comes out. But it may also go completely wrong if you choose 8 and say 4 to be in the same class, then you get a huge difference in the end. Okay. is clear with this pre-partitioning. So you try to just somehow perturb your differencing algorithm. You somehow allow to allow it to run with a simpler but equivalent initial condition, so to speak. And we're already putting things together. Good. Now this also defines the landscape, these pre-partitionings, right? Each pre-partitioning maps to a distribution of my items to the left and to the right side, and each such distribution has a fitness, so the whole thing is a landscape. And now I can compare how does the adaptive walk perform on my encoded landscape with the pre-partitioning and the original landscape that is just this spin landscape. And what you see is that, okay, now this this works much better. And in fact, after a decent time, they actually reach the ground state. So all the ones that
which is the
break
size
through
of
the
the
axis
sample?
here
Which
reach
is
the
the
ground
size
state.
of the sample you're going to?
That's 24. It's 24.
So what you do is you decide from the beginning which pairs or which subsets go together with the same class.
Yeah, but also randomly. I just say, okay, there can be at most n classes. So to each item, I assign a class from 1 to n. So there are some are just randomly together at the beginning.
And then you do the zero temperature taking.
No, then this is
process.
then to this pre-partitioning I apply the differencing algorithm. This gives me the direct solution, and that has a fitness. Yeah, but the landscape itself, the solution set, is now this class assignments.
And when you apply the evolution, you change the whole class.
But evolutionary mutation means that I assign a new class to one of the items.
Or you're telling you, because not that you interchange the whole class one to the other. So you change one item that was in one class into another class. So that the content of these classes are not kept constant along the evolution.
Yeah. So what happens and what now we cannot see is that many of these changes are just neutral. So many times you can just put things into different classes, but after applying the differencing algorithm, you get exactly the same solution as before. Okay, so we have a lot of neutrality. You can walk around a lot, see neighboring solutions, and once in a while you see one that is better, and then you take this. And so there's no proof, but I've never seen any realization that did not reach the ground state. Okay, for these limited sizes where I can also know what the ground state is. Good, so I think I shouldn't go much longer anymore. So what's the reason for this working better? Well, the first reason is that actually it enriches your good solutions, this kind of mapping. Right? So this is the cumulative density of states of the original problem. This is the cumulative density of states of the encoded problem. So there are many more pre-partitionings that map to the low energy solutions than to any others, which is also clear because you apply this differencing, which always gives you a solve. To enrich the good solutions, then you can ask yourself, okay, is this the only effect, or does the landscape in itself also have a structure that is interesting for evolution? And that is actually not the case. So if instead of doing this adaptive walk, which really does a mutation, you just in every time step draw a completely new solution. So you throw away your solution and construct something at random. And if this is better than everything you've seen before, you remember that. Then how long does it take to reach the ground state? Well, that is this curve as a function of problem size. Right? So this curve is just, okay, by randomly drawing solutions, how long does it take until I see the ground state? So that's basically the fraction of states that map to the ground state to the -1 is in principle the time it takes to do that, just randomly, and this is the time to optimize with the adaptive walk, when you say the scale basically the same and the random generation is even better. So, which means the only effect that comes from this pre-partitioning is that it enrich my good solutions, but the structure of the landscape is actually not very suitable for optimization, because when I follow mutations step by step, I take longer to find the ground state than just randomly generating solutions. Good. Yes. So now came the question, can we actually do that better? And this would be the last part of the talk, but I think I should just stop here or just go to the... yeah, let's just take this. Okay, so without defining things, I tried out the traveling salesman with a somewhat similar encoding, and also a maximum cut problem, which is another sort of spin glass problem. And to answer exactly this question, does the landscape structure give any benefit to optimization, or can you also just do randomly, or can you just randomly draw states? Okay, so here's the relative performance of 3 evolutionary schemes, namely doing an adaptive walk in an encoding, doing an adaptive walk in the direct landscape, in the original landscape. So this was the comparison we had.
So the performance is in terms of what, of time, or in terms of
I tell you in a minute. So this is that kind of comparison is exactly corresponding to this one here, right? We've seen something similar before. And then the third strategy is to just randomly draw states from the encoding and just remember what was the minimum cost or energy I've seen until then. Good. And the relative performance is the fraction of realizations where this particular strategy out of this 3 is the best one at this point in time. Okay, so you run many realizations. Well, many, it's 100, and the fraction of realizations where, for instance, adaptive walk is better or at least as good as the 2 others is this number here at a certain point in time. Good. And so what you what you see is, for number partitioning, it's really the best to just draw states randomly. So there's no particularly helping structure in the landscape, in this encoded landscape. And well, what we also saw before, the adaptive walk is still in the encodings definitely better than the one in the direct. But in the other 2 landscapes, there's some additional good structure that makes the adaptive walk actually better than just randomly drawing states. Okay, which now you can't really appreciate because I haven't gone through the definitions of all these.
What I understand is that the performance decays on time. I mean, if say, for example, adaptive walk for the traveling salesman finds a good solution, why then it finds a solution that is worse? Why the performance decrease?
Relative performance. So it's a fraction of realizations where this strategy, for instance, adaptive walk in the encoding, is better
than the other 2.
Than the other 2.
Ah, okay. Okay. So it's not that okay. It's not that it gets worse, it's that the other ones gets better, so.
But the sum should be 1. The sum should be 1.
No, because sometimes they are equally good. So when here for instance, right? So here actually at this time, basically, both adaptive walk and the random drift strategy, they have found the ground state, and so they are both equally good. And so I decided to count them as full. You could also say, if I'm as good as this other one, then I count as half good or something, but yeah. Good. So, the summary is that, okay, we looked at these landscapes to see what evolutionary strategies can do for optimization. Try to implement something analogous to genotype-phenotype maps into optimization, and so that it really can have a beneficial effect. First of all, in terms of sort of deforming our density of states, just enriching the low energy solutions, and that is the only effect in this number partitioning problem that we saw first. And then secondly, in other problems, you can also make the landscape smoother, such that you get stuck less often in local minima. And then also some of the encodings, although they look maybe complicated, they can be analyzed. And acknowledge my two co-author, Anita Mete from Calcutta and Peter Stadler from Leipzig, and funding from Partnership. Thank you.
So now we have Rosa and myself. We are trying to introduce a new scheme for questions, as which we already communicated to some of you. So if there are any questions by PhD students here at IFISC, they will get priority for the first questions. So any question?
So with encoding, you just have an encoding, and you have to find the minimum fitness for that given encoding. Mm-hmm. How do you do that? And then you will take the encoding. But for a given encoding, you obviously have to find the partitioning which gives you the best fitness, right?
Yes, for instance, by running these adaptive walks.
But the adaptive walks you do to change the partitioning, no? To change the encoding.
No.
So how do you change the encoding?
Not at all. I mean, the encoding is something that
from the beginning
so far we don't know how to define it in general, right? I mean, you just have an idea, okay, I find a somewhat larger state space and the mapping from that state space to my original state space.
Okay, so in the real example, you assign one encoding from the beginning, and with this encoding, you find the optimal solution.
Yeah, it's not that the encoding, I mean the alpha itself does not evolve. This is something that we have to engineer. So of course it would be nice to have a general recipe at some point. This is why now we're still in the stage of trying out different things to get a feeling of how this could work. But so far you just have an idea, okay, which kind of mapping from some other space could enrich your low energy solutions, make the landscape smooth, such that your adaptive walks can really find the ground state or at least low energy states.
And in this case, for almost all encodings, you reach the ground state. In this example, for almost all encodings you choose,
there are three, right? So there are three
in the first one, but the previously, previous transparencies, previous. More previous, this. So here it's
for each realization. Yeah. So I mean, a realization means I choose an initial condition.
An initial encoding. An initial encoding. The encoding is also random.
No, the encoding is the one that I described with this pre-partitioning.
But this partitioning is random.
Yes, but this is not okay. Just to get the terminology clear, this is not this is not the encoding. I mean, the encoding is this mapping alpha from one space to the other. Okay.
Yeah,
This is the encoding. Okay, and here you have states in your genotype space, for instance. Okay, I choose random states here. Then I use this alpha to calculate something in X, and that gives me a fitness. And then I know whether I should accept the mutation or not. And so the walk takes place here, and whether solutions are better or not, I know by performing this mapping.
This was a multiple question, but still.
Well, as far as I understand, those types of problems are important in large systems, right?
The first part of
Oh, these type of problems are important in large systems. So I've been wondering about the last picture you showed. How does it change for more, even larger systems? Because you're just in one system.
it just takes longer, right? So.
Yeah, but then they go and they cross each other. They go up and down.
Yeah, so this, I mean, for instance, here or there, it means, okay, in the long run, the adaptive walk in the encoding is better than the other two strategies. So it's really the best to do, to really play evolution on the encoding rather than going back to the original state space or drawing random states from the encoding. So this evolutionary scenario with the genotype-phenotype map is really the best in the long run. And if you increase the system size, yes, then it just takes longer.
So you expect the pictures to be the same, but just rescaling the time.
Well, I mean, for this one here, actually, I know it. So I mean, not for all system sizes, but for a number of system sizes, I tried it out. So this is now actually pretty large. This is 200, n equals 200. So this problem is a graph problem. You are supposed to cut the graph apart such that you cut the maximum number of edges. Put the nodes into two classes such that between them the maximum number of edges is running. So with graphs of size, random graphs of size 200, you get this picture, and with 100, yeah, these things just happen earlier. So that works.
So now it's variates.
No.
So you were first.
So the talking interdisciplinar, the perfect alpha would be something like diagonalizing the Hamiltonian, and then you go it represents the ground state of the Hamiltonian. So we see like this. So you are randomly choosing any basis or any system, so that when you find the eigenmodes or whatever, then it's correct. And go directly to a solution.
Yeah, well, let's say you somehow deform your state space such that most of your volume in the deformed state space has low numbers in terms of the Hamiltonian. So, yeah. And diagonalizing here is hard to say because everything is so terribly discrete.
So is there some kind of trade-off? So I mean, if you make the state space really, really large, then it takes very long for something to change in your phenotype, in some sense. Right? So I mean, if you make it very, very large and it mutates around, and it takes for ages to change something visible. So is there some trade-off that you would optimize for adaptability or something?
Yeah, this I don't know. I mean, what I know is that part of the literature on evolutionary algorithms advocates having sort of bijective mappings, such that really the number of solutions in Y in your genotype space and your phenotype space is the same, and you can reach everything. So just just a bijection, and in principle you only change the neighborhood structure. You have a different neighborhood structure in your genotype space. So this is going the other way, right? Making it really small in order to say, well, I don't want to have so terribly many solutions to search. I don't want to make my search space even larger by establishing an encoding, but this need not be the best way as we shown here.
So some redundancy is helpful.
Yeah, the redundancy is particularly helpful when it introduces neutrality. When all those solutions that map to this, all those solutions in Y, all those genotypes that map to the same phenotype, and they are also connected to one another. So you can actually walk a neutral walk, without changing anything in the phenotype, and then not changing the fitness, of course. Because then you can really explore a large part of your genotype space, and hopefully at some point see the way down, or up to fitness, if you like. So in principle, having this neutrality in an indirect way increases the number of available neighbors that you have, because at any point in time you have only n neighbors if your space is an n-dimensional hypercube. But if you can walk a long way without changing the fitness, then effectively you have many more neighbors.
How do you choose encoding? Because this picture shows which algorithm produces the best result, but if you choose different encoding, then wouldn't the results be different for these graphs?
Yes, so for these two I haven't even shown you what I do with the encodings because I didn't have time. As I said, so far they are sort of engineered in these three examples. You just come up with an idea that, okay, how could I enrich my low energy states? Maybe how can I introduce neutrality in my genotype space? So there's no.
These three graphs show one particular encoding, how it works. These three graphs, not just general encoding.
No, for the first one, it shows the one I defined with the pre-partitioning and differencing afterwards. And I can explain the other two.
But basically, graphs are for particular part encoding.
Yes, just like in nature also. There's chemistry and the chemical rules, which are based on the physical rules, do not evolve either, right? So chemistry tells you what an RNA molecule does. What is the minimum free energy state? So what will it look like after folding? So we are just.
So basically, these pictures could change completely if we choose different encoding.
Sure. Yeah, I can change it very much to the negative if I choose something very nonsensical. Then, so like for instance, enriching all the high energy states. Right? So then it makes it even harder to go to low energy just by chance because I choose the encoding such that it tends to map to high energy states.
You show that by this encoding, enlarging the basis of attraction of the good states makes the thing better at large times. What is the comparison with other methods of enlarging the expression space as simulating an analytic? Just allowing errors sometimes, just putting some finite temperature. Is this better or worse in some sense, or is there any easier way to do it?
We haven't done it. So in this original paper where this encoding was defined, they did it. So I should remember. No, okay, I can't say anything wrong. So also, I mean, the reason why we haven't, I mean, of course, we had this in mind, so sort of real performance comparison with algorithms that are on the market. But first of all, I guess we don't really outperform anything sophisticated here. So, that's also not so much the goal in the first place. We want to first explore these encodings and the role of neutrality, so on. So, as far as I remember, you can get a bit better in number partitioning if you go to non-zero temperature and actually run a temperature schedule. So simulated heating helps a bit also on the encoded landscape. But otherwise, we haven't.
So that was my question actually. But then I have a curiosity. Okay, shouldn't these numbers add to 1 in each case?
No.
It's already made the question.
So yes, they should. So the thing was that
no, look at t equals to 0.
What?
T equals to 0.
No, it's the same. It's the same.
On the left hand side.
yes, but there they do, right?
No.
Or what?
They are 2 about 0.5
Yeah.
or something.
Yes, okay. Yes, okay. Yeah, that's, where are we at time 1? Yeah, so this means that they haven't left the initial condition yet, right? I mean, so when there are, when there's a draw between 2, then I say that they are both winners. And so in the beginning, actually at time 0, which is not here because of the logarithmic axis, at time 0 they're all 1, because they're all the winners, because they're starting at the same initial condition for each realization and so on.
So, the take-home message is that if you are planning to crack a safe, you don't forget the laptop or something like that. So thanks, Konstantin. I think there's something prepared for yeah, so thanks.